Okay, good morning, everyone. All right. So today, before we start the class, I would like to confirm our midterm on next Monday is confirmed. Okay. So again, I repeat, our midterm, okay, for next Monday is confirmed. Okay, it is going to be conducted online, so that make sure that the midterm will start at 5 o'clock and end at 6:30. Okay, so the question you are supposed to answer should take around just 1 hour. There are only two questions. Okay, there are only two questions. One question 30 minutes. Okay, so two questions that will cover our power electronic devices and this DC AC converter. And then, like I said, it is MATLAB based. All right, it is MATLAB based. And then once you are done, okay, you can scan or use your handphone to scan, and then compile your result, your answer in PDF, and then make sure that you have access into CN because the question will be released from CN, and then your submission also to CN. Okay, so that is basically I said again, I need to stress again. I don't believe in two simulating exactly the same, okay, in terms of the drawing and patterns. So please don't do that, okay. If you do that, the consequences is I will divide the total number of the same, because I don't know who is the original one, right? You can just WhatsApp your friend, and then your friend WhatsApp your friend, and the friend WhatsApp. So because technology, right? I cannot stop you from doing that. Remember, I do have this complaint last year because I minus the mark or the similarity. Then the student aware of that, he planned to share his mark to his friend. For example, he share of the question. Of course, you see your friend who didn't know how to do will sure get 0. But if you give him, do you think he care about you? He don't care already, right? He just cut and paste and submit. Then what happened is that this friend are so kind to send the result to his own WhatsApp group. Then you know what happened, right? Let's say if say, I guarantee this one, I score full mark. Okay I friend with you, I share with you I get 2.5, right? Divided by 2. He already aware that But the friend say, I don't care, you are got result, let's WhatsApp group. Then what happened is that he sent to another 3 friends. So what happened is that it become 5, right? So the 5 mark I divided by 5, so everyone get 1 mark. And that friend thought that I divide wrong. I come, sir, I actually sent to one friend only, why you divide me by that? I said, wow, good, you come as, and tell me you are the one. I don't care, I say, I just show him that this is what I received. Then, of course, I believe he will curse his friend nicely. So, like I say, you want to help your friend, I cannot stop you. Whatever consequences you receive, don't come and complain to me because I mark according to what I see. All right? Okay. Thank you. Especially questions that related to your student ID. Okay, you send your friend, your friend won't change your ID. Okay. Now that is about midterm. Okay. And also the assignment I will also release by next Thursday after the midterm. Okay. Now before I release the what we call this release this assignment. Okay, I will later okay. I will upload this Excel form into Team. Okay. All right. So this is our whole class round. Okay. Latest we have a total of 115 students. 115. Okay. So like I said, you group yourself. Minimum 2, maximum 3. So let's say you group them in G1. Let's say this is group number 1. And then maybe this one is also in the same group, you put G1. Okay. And then maybe this guy is the group, same group G1. And then this guy is G2. And then maybe here is G2. And then here is G2. Okay, so this is how you group yourself. So from the list here, you can see who else already got group, who else don't have group. Okay, so please fill it up. I will upload now. Okay, into this okay, this is our team, right? Okay, this subject inside the file. Okay. Then maybe I will just create, wow, so many screenshots already. Okay. Okay. Okay, I will upload here. Okay, so you all can just double click open and put into your own group. Okay, so now what happened? Now we got 115, right? So meaning if the whole class every 13333, they will end up with only one student. Okay. So what happened is that this one student will need to find a group with 3 and split them up into 2. Okay. It cannot be 4. Okay, because I said there definitely will be 2 guys have nothing to do. So it has to be minimum 2, or unless you are bold enough to say I can do it alone, that is okay. Like I said, this assignment require you to do a model in Simulink and another software called Plex. So basically, the 2 students is one is doing MATLAB, one is doing Plex lah. The additional student coming in the 3, I don't know what you want to let him do. There, I don't care. You can ask him sit down, shut up, do nothing. That is mostly what happened. Really. Because during the demo, right, that is what happened. So I know that there are some say, sir, can we have 4? I mean, it never end. If I say maximum 4, you will say, sir, can have 5, right? And if I say maximum 5, sir, can have 7. I mean, in EMI, I allow 6. Design project, I allow 4. They will ask for 5. If I put 5, they ask for 6. So no ending. 3 to 2 is the best because if it's all 3 good, the remaining 2 will become a group. And now you got over like 30 group, right? With 3. If you are the first remaining one, please go and find a group that are willing to split to make a group with you. If this does not happen, then I will just simply find a group and insert you in. Okay, but please don't make me do that. All right. Okay. I will talk about the detail of the assignment next Thursday. Okay, I think yeah, talk too much already. It's time to continue because we are really lagging behind now. So what I'm planning to do is that I hope I can finish inverter today, which is almost not possible unless I skip all the simulation. Okay, now we have done a single phase, right? We done single phase. I forget to tell you all. I also done this what we call model in file exchange. That's why you only have a transformer at the back. So you can actually find it. I think I name it differently. If you want to see how this thing works in Simulink, right? I actually made it many years ago. I think I call it off-grid inverter. Here, pure sine wave off-grid inverter. Okay, so if you look at this, okay, so you can see this is the one of the simplest. Is that okay? We have a bridge, okay, and then we have a 24-watt battery. Of course, after the SPWM, right, the output here, you will have a transformer that convert, okay, the 24-watt or 12-watt into 230. Now the difference is that, like it shows here, okay, you will have a very big and huge transformer at the output side, and the advantage is that, okay, it's much more simpler, one stage. Secondly is that you will notice there is no LC filter here, okay, because the transformer itself will act as a filter already. So you don't need to have a LC filter at the back, okay, and then of course, yeah, you just need a transformer. Then you can also produce the similar output. Of course, the power or the current that it can deliver is really dependent on the size of this transformer. So by looking at the diagram here, the picture, okay, this is most probably like around 1 to 2 kilowatt, okay, of output power. See, similarly, like this one, you don't see a huge transformer, right? It's just a small transformer and of course one inductor lah. So like I say, it really depends on your, there is no right or wrong lah, okay? Every design will always have their advantage and disadvantages. It's about, okay, suitability, okay? It's suitable for what application? Okay, so you guys can have a download and try on this, okay? Okay. And then, okay, this is the other version. Okay, that is this one. So you see, you know, the principle is still the DC to AC bridge converter side. No matter whatever you change here, right? Like I say, as long as you know the 4 types of converter, it's just like a Lego puzzle. It's up to you how you're going to combine them. Then, you know, you are creating something new lah. Okay, then we go on for the grid converter. Okay, so grid converter. Okay, the important thing is the synchronization of phases, where we utilize PLL, okay, to do the synchronization. Okay, some equations for the LCL filter design, and also, yeah, the transfer function and the controller. Okay, last week, right, I said these R is quite small, 0.001. Okay, in fact, is the real value, right? Because I go and check all these data sheet. Some good inductor, they do provide you this R, okay? So it's between the value of 0.1 to 0.01 ohm. If you go and look at the inductor, okay, let's say 1 millihenry inductor. Wow, these are all very small power. Okay, usually we look for high power, which is 5 amp. Now see, inductor always rated in ampere. Capacitor is always rated in wattage. Okay, these are the high power version now. You see, it will tell you that 1 millihenry, 5 amp is 115 milliohm. Okay, so 1, 2, 3. So it's 0.1. Okay, this is the value. It cannot be 0. Once you put 0, then you can never get your Ki. Your Ki will become 0, right? So it has to, I mean, if like for example our case, like say it's between the value of 0.1 to 0.01. In this case, you just guess lah. I mean, just put a rough. Unless you confirm you want to use that particular inductor, then you can confirm the value. Okay, the rule is cannot be 0. All right. Otherwise, you can never get the P and I to give you a nice output. And like I said, this is only one of the methods. There are tons of methods to tune your PI controller. Okay. Okay, then we talk about application. Okay, or two of them. And now today we are going to move on to three-phase. Okay, like I said, three-phase just additional one phases. The rest is more or less the same. Now the difference here is, okay, very careful on this. Now we see that we have additional one arm, right? So we have 6 transistors instead of 4. Okay, and the transistor number, the upper side is always odd number, 135. Remember, upper side is always 135. The bottom is even number, 246. And then 1 and 2 cannot be turned on at the same time. Okay, otherwise they will short circuit. It's the same for full bridge. Okay, 1, 3, okay, or 1, 2, 3, 4. All right. Now in three-phase, we just need to add another arm here. Okay, so this arm is added lah. Now the difference is that there are 6, okay, switching state. Okay, there are 6 switching state, and these are the transistor. For example, state 1. Okay, now there are 1, 2, 3, right? So 3 bit. Okay, so it's 2 power of n. Okay, so that means a total we will have a 7. Okay, if we count 0 in, it's 8 state. So how come here we got only 6? Because the state 7 and state 8 is either all on or all off, right? So usually we don't do that. That's why there is no state 7 and 8. Okay, so there are 3 set of transistors. Okay, so that state 1 means that Q1 is on, Q4 is on, Q5 is on. Okay, and state 2, state 3, and state 4, state 5. Okay, let's see in detail. State number 1. Okay, this is what happened. Okay, 1, 4, 5 turn on. Okay, 1, 4, 5 turn on. All right. Now, when these 3 turn on, you will see this will be the output of the three-phase. Okay, so this is the part here. You divided a full cycle into 3 stages. All right. So now there will be 3 equivalent circuit here. Okay, mode 1, mode 2, and mode 3. Very, very important in the sense that, okay, now you look carefully. When the Q1 is on, okay, the positive is here, right? Negative is here. So this will be the source. So it go through A and C. Okay, it come here, go to A phase. Okay, when you go to A phase and then C phase. Okay, and then also at the end here, okay, at the end here, you will see it connect to B phase. So this one here will form an equivalent circuit of this phase A, C, and B. Okay, phase A, C, and B, the equivalent circuit. All right. So later from this circuit, we will derive the equations to calculate the value here. You will see that 3 phase, they will have different magnitude. See, different magnitude. All right. They will have 3 different magnitude. So this is state number 1. State number 1, okay, which is equal to mode 1. And then we move on to state number 2. Okay, state number 2 is Q, turn 1, turn on. So it come here, okay, it will go down here, right? And of course, at the same time, it will also go down here. So it's equivalent to this mode 2, okay? Equivalent to mode 2, all right? So again, you will have calculate this 1, 2, 3 for each phase. And then you move on again, stage 3, all right? Stage 3, which is mode number 3. In terms of circuit, you can see it's same. The only difference is that mode 2, the source is reverse. Okay, and of course, these two look alike. Mode 1 and mode 3 look alike, right? But the phase are different. This is A here, this is B here, and this is C here, and this is B here. And this is A here, this is B here, and this is C here. Okay, and the R value will be the same. We assume balance system. In three-phase, balance is very important. Once you have any unbalance, right, okay, it will cause problem to the entire grid. So we will try to, not try, the TMV has to make sure that we have a balanced system, okay? Of course, sometimes throughout the end of the distribution, we may have a little bit of unbalance, especially the residential area, okay? Because you see all the houses, right, you cannot ask everybody, hey, everyone turn on aircon now, and one turn off, you say, hey, everybody turn off, cannot, right? So there are some form of unbalance, but it's manageable. Okay, so at the grid transmission level, it must be 100% balanced. Distribution, LV, still can accept certain, I forgot already, how many percent of unbalance is allowed? Oh, too long already. Okay, there are some margin there, right? To allow this unbalance, because when you exceed those margin, you will have harmonic problem, you will have power factor problem, then a lot of things. Then you need to rearrange the network to make sure it is balanced. Okay. That's why in the residential area, right, the what we call the substation, okay, the PE, they have 3-phase out. When they connect to these houses, landed property, they really have to make sure that each of the phase is connected to the same number of houses. Phase A, let's say 20 houses. Phase B also 20. Phase C 20. Okay, so that this is how they maintain balance. Okay, 1 or 2 aircon on off, slightly different, because we are talking about for TMV is 750 kilo kVA . So 1 or 2 horsepower different, no big issue. Okay. And then this process, right, you can see 1, 2, 3, 1, 2, 3. And this process actually repeat at the negative cycle, okay, 1, 2, 3. Okay, now what is the difference of the negative cycle and the positive cycle? The difference is that, you see, now the positive cycle, the first one, we are talking about phase A, the reference phase. Q1, 4, 5, right? So if we go to the negative cycle, means that these 3 opposite, it becomes 2, 3, 6. See? 2, 3, 6. Okay? So it becomes 2, 3, 6. So similarly for this one, 1, 4, 6, the opposite cycle is 2, 3, 5. Okay? 2, 3, 5. Okay, and lastly, 1, 3, 6. Then the negative cycle is 2, 4, 5. Okay, 2, 4, 5. And of course, the rest repeat itself. Okay, the rest will be repeating itself. Okay, so the difference is that, okay, that means these 3 modes will be repeating. Okay, and this is how you achieve the output. So by this is still not PWM. This is just a normal, the square wave. For full bridge, you see a full square wave. But for three-phase, right, because of this three mode of alternate switching, you will have see something like that. I got a bit of steps. Okay, that means the harmonic will reduce a bit. Okay, will reduce a bit. So now we look into these three mode of equivalent circuit. Okay, by the way, you all understand this, right? Okay, you need to really stop, look at the slide, move one by one, then here and there, then you will see how the different. Of course, you can always refer to this table. All right, you have to refer to this table, and then yeah. In fact, this table is the most important. All right, if you can remember this table, right, mean you can actually, yeah, you should know how to draw this. You will see there is a pattern. You see the first one, state 1 and state 2, and state 3, the Q1 all turn on one, you see, for the positive side. The first three states is the positive side, okay? And the last three states the negative side. So negative side 1 become 2, you just go to the bottom transistor. So similarly, all right, the Q4, okay, the bottom one is Q3, Q3. Okay, and then the last one is 5 here, and then 6 here. So there is a pattern to remember. Okay, so now we look at the equation. Okay, so mode 1, mode 2, and mode 3. All right. So these are the equations. So you look at it, this is circuit theory, right? Very straightforward circuit theory, where R is to be same value. Okay, this is R equals. R equals mean that what? Okay, these two R are parallel and then serial with this R, right? So it's R divided by 2. When you parallel the two resistors, it becomes half, right? Okay, when you put 200 ohm together, it becomes 15 ohm in total. So 15 ohm the half plus R, right? This is how you get, and then equals to 3R divided by 2. So the equivalent circuit, okay, means that if you draw this, okay, this will be 3R divided by 2. Okay, and then now we want to find the current. Okay, the current I, right? So current I is very simple, right? You just need to the I is V over R, right? So you will have this is a Vs over R equivalent. So R equivalent is 3R over 2. You will have 2V divided by 3R. This is how you get the I. All right. Now, once you already get the I, you will know the voltage drop across these three transistors, right? So V equals to IR. All right. So VA and VC, that means the A phase and C phase are the same. Okay. So VAN and VCN is the same. Okay. Which is equals to VS divided by 3. Okay. VS divided by 3. And then the last one, the B phase, okay, the B phase will be negative R, okay, will be negative 2 Vs divided by 3. That is VBN. This is how you can calculate the voltage drop at all these R. Okay, and that will represent, okay, this what we call this the voltage level. Okay, it's Vs divided by 3. Okay, it's negative Vs divided by 3, and negative, again here is Vs divided by 3. All right. So this is how it works for the first or mode 1. Okay, any questions? the first thing is that remember this equivalent, okay, circuit. Okay, I believe it's quite easy to remember, right? Secondly is to know the phase A, B, C. Okay, and then of course B, C, A, and then A, C, B. Okay, the sequence lah. Okay, the sequence and of course mode 2 is always, this one is opposite. Okay, that is mode 2. Okay, these are the way to remember these 3 stages. Okay, these 3 stages. Okay, now we come to mode 2. The same process, you can see, the R equivalent circuit is the same for 3, no different, right? Because the circuit is the same. Okay, so the R is the same. So this one I believe is straightforward already. And then in terms of the I, okay, also the same, because the current, okay, is the same, right? So this one, second part is also the same. If I draw the line here, so don't confuse by the equation looks so complicated. As long as you know circuit theory, it shouldn't be a problem. The only difference is that you have to know where is your phase, the different A, B, C, all this, so that you can work this out. Okay, so in this case, you can see the positive is here, right? The A phase is here. So the VAN, right, is actually equals to, okay, I2 multiply by your V equal to IR, in other words, okay? Then you will get this, okay? 2V divided by 3, all right? 2V divided by 3 is just same as this one. The only difference is that, okay, the B here, because the negative is here, so you will have a negative sign. But here, mode 2, the positive sign is here. So you will have, there's no negative sign, in other words. So similarly, for B and C, right, you will notice that, okay, because the negative sign is here, so you will have a negative. So B, as long as these two connect together are the same, it will be B and C are the same, okay? And you look back at here, you can see it's actually the same equation, right? The only difference is that the signs are different, okay? The signs are different. Okay, now move on to mode 3. Like I say, the first two parts, same, okay? Again, in fact, the 4 also the same. The difference is that you just need to remember, you know, either the A, B, or C, okay? So that is the main differences. So in other words, if in the final exam, I ask you to calculate the 3-mode voltage, right? I will give you the voltage, so let's say 10, 12 watt. Okay, I will give you 12 watt. Okay, then even though I didn't give you any resistor value, because at the end, right, you can see it will be cancelled off. So you just need to have, like, for example, in this case, you just use 12 watt divided by 3, or 12 watt multiplied by 2 divided by 3, so that you will know the voltage, okay, at each of the phases, okay, at each of the phases, okay. So with that, you can easily actually draw out, okay, you can draw out this, waveform, okay. Okay, up to this point, is it okay? Any questions? I don't know lah. Is it very complicated? I don't think so, right? I mean, you can pass circuit theory means you should be able to solve this lah. Okay. Let's move on. Okay, now let us see if we want to do that in Simulink. Okay, so now in full wave, we just need one pulse generator enough, right? We just need one pulse generator. But now we got 3 phase. Three phase, we need 3 pulse generator, okay? And each of them will have a, what we call the opposite side, the NOT function, okay, the NOT function. And then the difference is that each of these, right, will have a phase different. Okay, this one is 0 degree, no phase different. And this one is positive, 120 degree. And this one will have a negative 120 degree phase difference. Okay. So the only difference is these 3 generator will have these 3 phase difference. That's it. Okay. And then now you got 6, right? Output. And this 6 output, okay, of course here if you want to implement, you can key in the, you know, what we call this, all right, the phase difference here. Okay, so it's still 50 Hertz. Okay, no modulation, still no modulation yet. Okay. And then you will produce this output. Okay, you can see the first one, okay, 50 Hertz, right? And then this is the negative part, which is the complement or the not inverted part. And this one, so this one is go for Q1, Q2. And this is Q3, Q4 for the second phase, right? And then it's just like Q1, Q2 is for phase A, Q3, Q4 is for phase B, Q5, Q6 is for phase C. All right, so you can see there will be phase difference. Okay, you can see that they are phase different. They are phase different. Okay, from the phase A. Okay, 120 degree lah. 120 degree. Okay, I think we will skip this exercise. I mean the wet lab, just to make sure. Okay, now for calculation. So what is the RMS fundamental line voltage? Okay, so the RMS value, okay, of the line voltage is governed by these equations. So you must have a VS, which is your DC source, 4 multiplied VS, okay, sine 60 degree, and divided, okay, by square root of 2 multiplied by pi. So you will have this 0.7797 multiplied by your VS. So in other words, if your VS is 100 volt, okay, your RMS fundamental line voltage will be 77.97 volt. Okay. And then the line through neutral voltage, okay, can be found by this equation, which is square root of 2 multiplied by VS divided by 3. So what is the difference with the line voltage and the line to neutral? Now in 3 phase, right, we always say we have 230 watt from our power socket. Okay, so that is actually called the phase voltage, because we only receive one phase. So we call phase voltage. Okay, phase voltage. And then we have a term called line voltage. So line voltage is 400 watt for Malaysia. Okay, so we have line voltage and phase voltage. So line voltage referring, okay, to the voltage. Okay, for example, our voltage, okay, is what we call a star. Okay, 3 phase, right? Okay, yeah. Okay, the line. Okay, we have phase A, phase B, and phase C. Okay, so line voltage means that the measurement between these 2 points, A and B, we will have 400 watt. Okay, that is the line voltage. When I always talk about 132 kV, 11 kV, 400 watt, 275 kV, these are all referred to line voltage. Okay, they are all referred to line voltage. And then phase voltage is here. A to neutral, the center point, the N. That is 230 volt. Okay, that is the phase voltage. So C phase to N 230, B phase to N also 230. Okay, so that is the difference between line voltage and phase voltage. It's important, especially when you're dealing with three phases. Okay, so the conversion between them is actually governed by the square root of 3 lah. All right, it's governed by the square root of 3. All right. So now for this inverter, right, you will have these two equations. One is the phase voltage, one is the line voltage. Okay. Okay. So now we move on. Okay, to this one. Okay, we already have a pulse generator. Now we got 6 lines come out, and I said Q1, Q2 will be the first two one. You can see it's quite easy to remember to connect. Q3, Q4, Q5, Q6. All right, and then we have a 3-phase resistor, and we measure the voltage, and this is the N. So this is the phase voltage, right? We measure with respect to the neutral. So we will see, okay, the output of RMS here, and of course we can see the waveform here. So it looks more sine wave than the normal single phase bridge. Okay, this is the without any modulation. Okay, without any modulation. Okay, so this is how it looks like. If I can just show you. Okay, this is the MATLAB. But we're going to skip this one. For you can do it at home. Oh. Okay, I put 600 watt here. Okay, I put 600 watt. And then I think I already run it. So we just see the waveform. You'll get around 282. Okay, so this will be the output of the 3 phases. You will notice there are phase difference. Okay, of what we call this 120 degrees. Okay, phase difference of 120 degrees. As you can see that. Okay. So it will be something like what the textbook is showing lah. Okay, what the textbook is showing. All right. Okay, now we move on to the SPWM. As we know that you want to reduce a harmonic and you want to produce especially sine 3 phases. Okay. If you want to connect to the TMB same, or they're looking for a sine wave, okay, of this what we call this modulation. So similarly, okay, we already have the block that will allow you to generate, okay, this SPWM signal. Okay, when you open up, remember you have to change to 3-phase bridge. Okay, previously is the full bridge. Okay, yeah, I think it's single phase. Okay, of course, switching frequency. Okay, of course, this is just for you to see lah. Otherwise, practically, it should be more than 1000 and above lah. Okay, the rest, okay, 50 Hz. Modulation index okay, 0.8. Okay, the whole thing is the same, huh? The whole thing here is the same, okay, except the modulation. You just change this block, okay, you just change this block. Connection, everything same. So one is done, okay, this is what you see. Okay, of course, this is 500 Hertz, so you can see, you know, different, yeah, you can see more clear. Of course, this one is 10K, which is much more practical. This will be your output of your modulation. Okay, so this is 2 levels, okay, of these modulations. And then, of course, you can use this right away for any AC drive. Okay, unless you want to connect it to the grid. Off grid, again, is the same. You just need to use the L and C filter. You want to connect to the grid, you have to use LCL filter. Okay. Okay. So now we move on, okay, to the application. Now, same, variable speed drive, variable frequency drive is the same, but now we just talk about 3-phase lah. Okay. So Schneider product is French, so they use variable speed drive. Variable frequency drive is more on US. Okay, same thing. You have a rectifier, and the DC to AC is to have 3-phase to control 3-phase motor. Okay, same working principle. Okay, like this one. We have a single phase. Okay, let's say I want to control a 3-phase motor with my single phase power. Can or not? Can. You buy this single phase to 3-phase VSD. That means here you have a single phase of 230 volt. Right? It rectified, okay? It becomes DC here. Okay, so it's AC here, DC here. And then here, DC back to AC, right? But your motor is 3-phase, so you need to have a 3-phase, okay, what we call this inverter, okay? So with that one, you can control a 3-phase motor. Similarly, you control the frequency here, you control the speed of the 3-phase motor. This is how you can, you know, there are many small factory or small shop lot especially lah. They don't have 3-phase, right? But they buy a machine, require 3-phase to run, right? So how? Okay, so you can recommend them, okay, we get a VSD that will convert the single phase to 3-phase so that it can drive your 3-phase motor. Okay, you don't tell them, oh, I also don't know. You go and rent an office with 3-phase lah. Okay. So similarly, okay, we will have a 3-phase in. Okay, this is a 3-phase rectifier and also a 3-phase output. So 3-phase in, 3-phase out. This one normal lah. The only thing is that you can control the speed. Okay, so you can control the speed. So this is the immediate application, okay, for the 3-phase, I mean, what we call this drive. Now in practice, apart from, okay, this drive are basically water pump, AHU, like I say, air conditioning system for big building, AHU, okay, water pump. I don't think the inverter aircon for the houses one is still running on single phase. And of course, one of the prominent application is EV. Okay, now today we talk about electrical vehicle, right? Okay, the EV. Now the EV, one of the classical is, okay, Nissan Leaf. Nissan Leaf motor is a 3-phase motor, AC, 80 kilowatt. Okay, of course, our car, right? You cannot expect them to, when you press the accelerator, it go max speed, right? No way. You need to control, right? So there's been every EV, there is a variable speed drive inside. Okay, So there is a variable speed drive. You step the pedal, you are controlling the speed drive frequency. So it will control the speed of the motor, right? So it will control the speed of your car. So you can see that when you open up the EV, this is how it looks like. The engine. Okay, if you look at this race. The bottom part here, okay, is the motor. The motor is really take very small part only, half of the engine. On top here, it's actually all the DC-DC converter lah, integrated charger lah, and at the bottom of this DC-DC converter is the inverter. That is the three-phase inverter we are looking at. Don't be surprised, it's so simple, it's only that 6 transistor. But they sell you, how many thousand lah? Okay, because they are not just sell you a product, they sell you knowledge. They convert their knowledge to money lah, in other words. Okay, so okay, the basic concept is that, okay, you have a battery, they go through a DC-DC converter, which is the one on top, and then the DC-AC converter, okay, to the motor. And of course, they are bi-directional. The motor can charge back the battery lah, okay? So they'll like say, this is the battery pack. They put under the seat of the car, okay? And then that is how, you will notice that when you open the EV, right? The cable with the orange duct, okay, represent electric power. It's just like our conduit. When you look at the building, right, the red color pipe is mean for water, bomba, firefighting. And you see the pipe with orange color means it's for electricity. It's a world standard lah. You color it red means electricity. You see, orange is electricity. That is Nissan Leaf. Okay, so only 80 kilowatt of power. All right, it's not very heavy lah. Around 58 kg for the entire motor, and it can have a speed of 10,390 RPM. Okay, and the torque is quite strong, high, 280 Newton meter. So that is one of the application. Secondly, okay, Nissan is normal car. You see, nowadays we talk about Tesla, right? Oh, sport, man. Yes, Tesla also use the same thing. The only difference is that you can see the motor. The motor is double, 193. This one is only 80. Of course, you can accelerate to 100 less than 4 seconds. Okay, and then in fact Tesla have two motors. Okay, it's just like 4-wheel drive. It got front and back. See, it got the rear motor, which is a little bit lower, higher power. Front, okay, also sorry, front is the lower, rear is the higher power. Okay, they have two motors, one front, one back. That's why it has so strong, okay, and powerful. And when you open up, right, so what you see is this. Okay, this is one of the real engine, the motor. Now you will notice that you thought there are two motors here. No, no. Remember the orange color? It means that is the power. You can see this is the power connection. In fact, one side of them, right, is here. You open up, it's an inverter. You can see this is phase A, and this is phase B, and this one here is phase C. Tesla make it in the way that it makes maintenance cheaper. You see, if you buy Nissan Leaf, if the inverter got problem, they say, oh, sorry, you have to change the whole thing here. Shit, right? Change the whole thing, 3-phase, usually all this drive, they don't spoil all 3-phase together. They usually spoil 1 phase. Like you see, what happens is that your switching got problem. When these two turn on together, short circuit, right? Then these two transistors burn. So that means only this phase spoil. These 2 phase still okay. But if the old way of car, You have to change the whole thing. And Tesla consider that, say, never mind. If your phase A got problem, they just change the phase A part. Take out the whole board, put it back. Cheaper maintainer, right? Okay, and easy maintain also. So yeah, that's why it can be so cheap. Okay. And then the another application is for train. Now for train system, they are AC train and they are DC train system. Okay, the AC DC train doesn't mean the train motor is AC DC. Both train are also, the motor are AC. The AC and DC train means that the power delivered to the train system, okay, like our MRT, LRT, Rapid, Putra, they are all DC train. Means that the power connected to the train is DC. That's why I call DC train. But the motor that is running the train is still AC, okay? And then AC train means that like our KTMV, Shinkansen, all the long range train, okay? The power that delivered to the train is AC, okay, called AC train. So again, the system is still the same. Okay, take this example. Power from the grid, okay, it convert to AC to DC, okay? And then, of course, these are DC train, what we call example lah. So when you get into, okay, this part is usually inside the train already. DC, DC, okay, and DC, AC. And then you control a motor, okay? So you can see these are the train. Now, where are all the train inverter? They call it traction inverter. Okay, so you usually put at the bottom of the train, at the bottom of the train. Okay, so the inverter is there. Of course, there are usually two motors, one in front, one at the back. Okay, of the train. Okay, so again, they run in 3 phase. Okay, similarly, they will still use a 3-phase inverter. Okay, to run the train. Okay, to run the train. So you can see the line that is connected to the train is either on top or at the bottom of the train. Okay, at the bottom of the train. So that is all ACF for metro rail. So these 3-phase have major application. Okay, the major application. Okay. Okay. So after this, any questions? Okay, we have modulation, we have non-modulation. Okay, application to EV. Like I said, in the old days, I mean, in my day of study, we don't have EV. Okay, we only know that this 3-phase is used in train. Okay, back then Malaysia still don't have train. Okay, in 1994, I think 93, yeah, when I was studying my degree, for us train is something very strange in Malaysia. Even you know how to study, you come back here, no job for you. But now different already. We got so many MRT, whatever they are coming out. Okay, because we are trying to move to a developed country. Okay, so train is a very important infrastructure for any country that want to become a first world country. And then what is driving this train is electricity. Okay, the train traction power and the motor. Okay, back then because of battery, okay, storage is not strong enough. That's why no EV. Train can because it's connected, it's a wire. But now because of the advancement of battery, EV is possible. But still they cannot get away from inverter. But of course, you need some innovation, how to put the whole inverter inside a car, and then you see the difference is that Nissan, right? Okay, the inverter is still like in the front bonnet. You open up, you can see the inverter, right? But in Tesla, it integrates just next to the motor, Okay, in fact here, this one is the inverter. And the motor is here. So it's safe place. The more that you open it, it's almost empty, you know. I mean, some electronic parts. Okay, so we will see. Okay, because I think for Malaysia, we need to wait for another 10 years for this EV to really come into our market or our daily life. Okay, but don't think they are like another 10-year bullshit. Don't want. I mean, you know this knowledge, it will be useful for you. Trust me, when this thing come into Malaysia, all those Toyota, Honda, whatever service center will require someone with electrical knowledge to service their car. Now they will say, no, sorry, we need mechanical engineer, right? They don't need electrical engineer to service car. In the next 10 or 20 years, it's going to be a trend. Okay, it's going to be a trend. Okay, now we move on to grid connected inverter. Now grid connected, like I said, you need what? PLL, right? No problem. SPWM, right? No problem. The inverter, okay. Now the catch is here. You need, when you want to control three-phase, you need to do this transformation called Park transform. In short, they call it ABC to DQ. I'm not sure you study this or not. Have you all? Park transformation. Oh no. Okay. Never mind. This one can count in final already, since you all never study. Okay, Park transformation is to convert the ABC phase into a DC, D, and Q output. D stand for direct, represent real power. Q stand for quadrature, stand for reactive power. So you are converting the three phase, okay, CR, PLL, and then you convert it to 2 DC, D here and Q here. D represent real power, Q represent reactive power. Then you control the current. ID is the real power current you want to inject to the grid. IQ is the reactive current that you want to inject in the grid, right? So you can see this is a feedback system already, right? So this is a plus, this is a minus, plus, minus, and of course the PI controller. So the PI controller, you output, you go back to DQ, transform back to ABC, back to its three phase in other words. Then of course the output of ABC go into SPWM inverter. And then of course LCL filter and connected to the grid. So you control how much real power and reactive power by controlling these two current. And of course the feedback here will be again the same like the first. You need the voltage to know the phase angle, and then you need to have the current, okay, to convert the ABC to DQ. All right. Now ABC to DQ, there is a equations to govern it. It's a transformation, okay, from this one is ABC to DQ, and this one is DQ to ABC. Okay, DQ to ABC. It's just like the symmetrical power transformation, right? You have a positive sequence, negative sequence, and zero sequence, right? From the ABC to negative sequence, okay? So in power system, right, that is very important. You want to know positive sequence, negative sequence, and zero sequence. So this one is Park transform, ABC frame to DQ frame. Now, if you want to see this, okay, maybe I will write this program. Okay, so now you see this is our three-phase in. The orange line is the time that we measure. Now you can see this is the three-phase in terms of the phases. Now A here is the highest, right? Because the A is at the top. Okay, and the yellow phase is here, and the blue phase, okay, is here. All right, and then once you go through the equation, you will see there are two DC lines. It becomes just like DC. But one represent of real power, the red color one, okay, which is D, and then reactive power is 90 degree different, right? So you can see the blue one is actually Q. I put a dotted line here. So what happened is that when I move, you can see now, okay, until this point, you can see, okay, the light blue is the vector, okay, and then you can see if I click a play button, you can see it continue to move. Okay, so this is how it works. So this is the rotating frame of D and Q, and this is the ABC frame. Okay, with respect, okay, to this what we call this three phase. So it's just a simple matrix transformation. Oh, this one I also forgot. I didn't upload yet lah. Okay. So it's a really very clever transformation. This guy is called Park, right? And you look at these are the equation I use, okay, to do the transformation. So this equation here I use is actually derived, okay, from the matrix here, okay, from the matrix here. That means I get at any point of A, B, and C, right? Okay, the A, B, and C. Okay, because three of them will not be the same, right? At the point, then you just substitute in, okay, the value. Then you will get, I mean, multiply lah, okay, with all this, you will get the output at DQ. Okay, similarly, you want to convert back, you put in the value of D and Q, okay, then you can get back your A, B, and C. And this is one of the ultimate tools used in our current many three-phase inverter. Because this is really a very good design. Now, if we look at the Simulink again, okay, now this one is exactly the same except I change this to three-phase. This one, of course, LCL, you need to have three inductor, three capacitor instead of one. So L, C, L. Calculation-wise, same equation is applied. Okay, then we connect to a DMB three-phase. Then you look at this. Okay, first of all, remember, we need to have a PLL. The feedback of the voltage, or the grid voltage here, will come into the PLL, right? So you look, it's exactly the same here. Feedback of the voltage come back to the PLL and go into the buck transform. See, go into the buck transform. Okay, MATLAB already have this buck transform. And then the feedback of the current, okay, the feedback of the current here, okay, will get into the buck transform as well. Okay, this is the phase angle, WT, omega t. And then the output is DQ, right? So you split out, the top one is D, the bottom one is Q. Okay, the zero is zero, we just terminate them. And now, okay, I don't want to inject any reactive power, so I put 0. And I want to inject some active power, so I put some value. Go through the P and I, combine them back to D and Q, and then I transform back to A, B, C. Okay, and of course, normalization. I need to know normalization, and then SPWM. And this SPWM will just connect here. Okay, so if everything is fine, you should be able to get the output of both sine wave, okay, of voltage and current. Okay, that will allow you to connect it to the grid. All right. And then you can see that the total harmonic distortion is only 1.73, which is lower than the TMV 5%. So meaning that, this is how the solar inverter is working now. Okay. Injecting the voltage and current, okay, into the grid. Both, okay, in sine wave. All right, after the LCL filter. Okay, after the LCL filter. Okay, let me see. This one, I think we got a three-phase grid inverter. Okay, this one, okay. This one I got upload. Okay. So you guys can try to download this, and at least today you can run some MATLAB because I need to really speed up the whole thing. Okay, three-phase inverter. Okay, you all here, you just type, let's say three-phase grid inverter. Three-phase, you will see Rodney Tan. Okay, and then yeah, you just download lah. Okay, you please download down while I'm explaining. Okay. So okay, when you download, okay, I already make the control into the blocks here, red color. And then of course you can double click to see what's inside. Okay, I already do some mask setting so that you can control the switching frequency, the PI control for both. Okay, but if you want to see inside, okay, it is something here. Okay, this is a much more advanced version of what I show in the slide. Because after the DQ, right, and after the PI, I did some decoupling to make sure it's much more stable. I just add these two parts here, but don't worry, like I said, okay, the working principle is the same. So it may take a little bit longer time. You see, as your system become much more complex, right, it will become more time consuming, I would say. Okay, while waiting for running, I think we are done already for DC to AC. Okay. Yeah, of course, one of the application is the grid inverter. Okay, that is connected to the grid. Okay, high power grid for wind farm or the PV farm. Okay, when we are talking about central inverter means, we're talking about 1 mega, 5 megawatt and 10 megawatt of grid inverter. No longer a very small one. And then, okay, like I said, yeah, this one is not in the cost outline, but at least I'd let you know that apart from the inverter we are talking just now, there is a multi-level inverter. Sometimes we call neutral point clamp, so NPC. We have NPC inverter. The difference is that you can see there are two transistors connecting instead of one, right? So this is 3 level. 3 level means that 2 transistor plus 1. Okay, so it's 3 level. Okay, this still you can see quite an advanced inverter they're using. In the research community, it can go up to seven level for one of these, representing one switch. All right. So I will, yeah. If I want to talk about this again, not enough time. Guarantee not enough time. But the principle is the same. Okay. Rest assured. Doesn't mean that, wow, sir, you never teach it. I put 10 transistors also same, right? You on together, you just like the Q1, Q2, Q3, Q4 thing. Okay, don't be scared by looking at the transistor here. Remember, when you want to increase the power of transistor, parallel, right? Increase the power, the current is parallel, increase the voltage is serial, right? It's the same thing. That's why you see, you may ask, how come the Tesla inverter bought so big? 6 transistor only, right? No, you open, it may be 12. Because they want to increase the power, remember? Because transistor 1 not enough. Okay. So it could be in the form of this multi, but I don't think so. Because for train and car, right, they don't have neutral line. They just use the delta the delta line. So this one is meant for system with neutral line. Okay, so you have to know that. So what I have teach just now is good enough for the EV system, but I'm not sure about the future one. Okay. Okay, so with that, we should be able to conclude, or this one is halfway done, our DC to AC converter. All right. Any questions? Okay, let's go back to our, okay, I think it's done already. So yeah, you can see the output here. All right. We have both sine wave output. Okay, you go in, you can see, okay, the both sine wave, okay, voltage and the current, okay, the voltage and the current output. And you will notice that for 3-phase, right, the current is easily talk about 100 amps, okay. So you can actually control, okay, your current here, how much you want to inject, okay. All right, so okay, so we are done, okay, with this chapter. Okay, like I said, the midterm will cover until this chapter. All right. And then, yeah, next week midterm, we release assignment on Thursday, and then we shall start DC-DC converter. Okay, by next week already. Okay, because week 9, week 10, 11, 12, 13, 5 weeks, I need to finish 3 or wow. So we have to skip a lot of this simulating thing. But like I said, I'm doing this for the first half is to prepare you all for the midterm. Okay, and of course, you can always do it at home, right? For this, for your own knowledge. But don't worry, even I skip, I will still ask you all to do at least one in DC-DC, AC-AC, and AC-DC, right? So you will have some familiarity on it. Okay, so any questions? Online class? Hello? Simase?
No, sir. All good.
Okay,
Yes, all good.
we got tips. The tips already given, right? Okay. All right. If no, then we will end the class today, and make sure don't be late. Okay, please come into the class 15 minutes earlier okay, because our meter start at 5, right? I will be inside there in 4:45. Okay, so the midterm will start sharp 5 and will end sharp 6:30. Please don't miss this midterm, okay? If you make me to set another set of questions just for you, for some reason you didn't attend, wow, unless you have a even you have valid reason, I need to set another set, right? So you're making my life hard, right? So I will make sure that the question is harder than this one. That's what I can say. You want easy question, please come next Monday. Okay. All right. Okay, so if no question, then yeah, we will end the class today.